Here is the solution for problem 4. So problem 4 is a seesaw with a fulcrum in the middle. There's two masses at each end, m1 and m2. And the Lagrangian is given by the kinetic energy, total kinetic energy, which is 1/2 m times the velocity squared of each one. Now, since this is rotational, purely rotational motion, so the masses are not going, they're not going in and out like this, they're just rotating about the fulcrum. The only kinetic energy term is that rotation term. So for mass 1, it's 1/2 m1 times this length, which is L over 2 times theta dot all squared. So for mass 1, you have this kinetic energy L over 2 theta dot squared, and same for mass 2. So it's 1/2 times this is the velocity term times the sum of the masses. Then the potential energy is given by the height of each of these. Now, as theta increases, the height of m2 goes up. So how much it goes up is L over 2 times sine theta. Now, the Lagrangian is minus the potential energy, so the minus shows up here for m2. As theta increases, m1 goes down, so the potential energy decreases or goes negative. But again, the minus cancels out, so you get a plus here. So the total Lagrangian has these two terms here, the kinetic energy term and the potential energy term. Taking the partial of L with respect to theta, you get this first term here. And taking the partial of L with respect to theta dot, you get this term here in the square brackets. Taking the time derivative of that, you get a theta double dot. And if you rearrange things all nicely, you can get the formula for the motion here is theta double dot equals 2 times the difference in masses, g cos theta, over the total mass times L. And if you move this L over to the other side, you'd have an L theta double dot. That's kind of like a motion, a linear acceleration motion. So how fast the mass is moving. That's maybe a more familiar form. And you can see that it goes as g cos theta, which makes sense because as theta is at a horizontal, then the acceleration is greatest. But the net force is the difference between these two masses, and the net acceleration depends on the sum of the masses, which is the total mass for the system.